Hi everyone. So now I'll be speaking about Shapeless. Before starting, can you show me how many of you know that there is a Scala library called Shapeless? Okay, great. And now can you raise your hand if you know how to use it and how it works? Okay, that's a pretty low ratio. It was expected. So first, a little bit of introduction. My name is Valentin. I come from France. I've been using Scala for about 4 years. And recently, I made a very humble contribution to Shapeless. I added a feature that probably nobody will ever use. So what is Shapeless exactly? It's a Scala library for generic programming. It started 5 years ago by Mike Sabin, and now it has about 70 contributors and about 40,000 lines of code. So what is generic programming? Generic programming is the art of programming for type that you don't know nothing about. Okay, it's not like the classical polymorphism that you usually use, because you want to be able to program for type that don't exist yet. And so you will get much power out of generic programming because you will be able to erase much boilerplate for your code. So how it works? Basically, you transform a business type into a generic representation. You write a program that manipulates that generic representation, and then you convert back the modified generic representation into your type, your business type. Of course, Shapeless is not the only way to do generic programming. You can do generic programming with the Scala Reflection API, where the generic representation are the types of the Reflection API. But of course, nobody wants to work with the Reflection API. So, Shapeless. One of the basic blocks of the generic representation in Shapeless is the heterogeneous list, or HLists for short. It's a kind of list that can contain elements of different types. And more importantly, the type of the HList retains or reflects the type of each of the successive elements in the HList. The definition is very simple. It's just a sealed trait, HList, with two implementations, HNIL, which is an object, it's unique, and it represents the empty list, the empty HList, and a case class, colon, that has two type parameters, head, H for the head, and T for the tail, which is a HList. And it has two fields, the head and the tail. So, using this definition, we can create HLists with a syntax that is very similar to standard lists. But of course, you can put different types in the list. You can also define type aliases with the same syntax. So you can, here LSB is a type alias for long, followed by a string, followed by Boolean. And of course, if I want to assign my first HList there to something of type LSB, it wouldn't compile because the two HLists don't have the same type. So how do you manipulate HLists? The problem is, as we said, there is no method in HList traits. So there are pretty much nothing you can do unless you saw the talk from Pavel this morning and you know about type classes. And in fact, type classes is the mechanism through which we inject functionality into the HList. So let's see how we can, for example, count the element of a HList. The size of the HList is known from its type because we have the type of each of the elements. So we should be able to do that. So we define a very simple class, size. Can everybody read on the screen? Yeah? Okay. So we define a case class size, which has a type parameter L, which is a HList, and a field that will give us the size of the HList. Next, we define the companion object of this case class, and that's where we will put the implementation of our type class. So first, we say that HNIL has size 0. Okay, so we create an instance of size for the type HNIL with value 0. And then we say if our list is not empty, and if its head type is H and its tail type is T, and if we are able to compute the size of the tail, then the size of the whole HList, H colon colon T here, is simply 1 plus the size of the tail. Okay? And finally, we had a little convenience method that allows us to pass a HList, grab through implicit resolution, grab an instance of size, and simply return the value. Okay? Is that easy? No? Too bad. Okay, let's try it out. So we have our apply method. We can pass a little HList to it. And of course, it returns 2. Okay? Let's see how it works. When we call size of foo followed by true followed by HNIL, the compiler requires that we provide an implicit instance of size of the type string followed by boolean followed by HNIL. Fortunately, we can obtain this instance by calling hconsize with type parameters string and boolean followed by HNIL. But to call this method, we need an implicit size of boolean followed by HNIL, which in turn is obtained by calling hconsize with type parameters boolean and HNIL. Then it requires a size of HNIL, but we already have provided its HNIL size. And so finally, when we call size of foo followed by true followed by HNIL, the compiler synthesized the call to hconsize of HNIL size. And so finally, we create a size of 1 plus a size of 1 plus 0. And we get its value. Okay? And that's why we obtain 2. Is that easier? Yes? Okay. So to sum it up, to manipulate HLists, we use its recursive definition, we decompose it recursively, and we let the implicit resolution mechanism do the work for us, okay, and do the real traversal of the HList. So, okay, it's cool, but we won't be using HList as our business object, right? So we need something to transform our classes into HList and back. And that's the work of the generic class in Shapeless. With internally, it uses macro, but we won't looking at that. And generic takes a case class and provides 2 methods. The method 2 that takes an instance of the case class and returns a HList, and the method from that takes a HList of the right type and returns an instance of the case class. Okay, so it goes back and forth into the generic world. And of course, I can interpret that. I can say, make me a Marge Simpson, perhaps. and I get an instance of person. And if I pass the wrong type of HList, it wouldn't compile because it's not the right type. We cannot build a person out of it. So now we're ready to look into more real-life use case. So imagine you have the task to tell your boss what have changed between now and the last backup on your database. Or maybe you are writing a test framework and you want to provide very precise feedback to your user when the actual result is different from the expectation. Of course, you will have to handle many classes that are not written yet. And you cannot do this by hand by comparing field by field by hand. So that's a mission for generic programming. Okay, so we'll try to do that. So basically, we are building Delta, which will be lists, or rather HLists, of this diff algebraic data type. We have a sealed thread diff that has two implementations. Either it is identical, both fields have the same value, or it is different. Okay, and we have a little factory method here to compute a diff of two elements of type A. So now we implement our delta. So first we are creating a type class here. Okay, in Shapeless there is a superthread called depfn, which has multiple declination: depfn0, depfn1, depfn2. That stands for dependent function. It's a kind of function whose return type varies according to the input type. And that's why here we have to define an abstract type member named out. And here we say, okay, we don't know yet what the result type will be, but we know it will be a HList. Okay, the plan is to pass to this type class the representation of the object the generic representation of the object we are comparing, and it will give us the HList of diff. So before we can start to implement this type class, we have to, we don't have to, but it's very convenient to define a type alias. Classically, it's named aux, and it just adds a type parameter that refers to the abstract type member. It's convenient because sometimes you want to grab the out type from an instance of simple delta. So you will do myInstance.out. But sometimes you want to constrain this out type, and so you will need to pass it as a type parameter. So with this aux trick, you have both the possibilities. Okay? So next we will do the recursive algorithm like before. We first say that for HNIL, the output will be HNIL. Of course, comparing two empty things, it's obligatory, it's mandatory empty. And then the non-empty case, where we say, okay, both my representations will have a head type H and a tail type T. And probably there will be a delta for the tail, and this delta will output a type DT. If I have that, then I know that I can make a delta for H colon T that will be a diff of H followed by the diff for the delta for the tail. Okay? So I can implement that. It's quite simple. The trait depfn only define two abstract members, the type out and the method apply, that has 2 parameters for depfn2, 1 parameter for depfn1, and 0 parameter for depfn0. So of course, if I am to compare two HNIL, I will return HNIL. And now, if I compare two non-empty HLists, as I said before, I will return an output of type diff of h followed by dt. And it's obtained like so. I call my factory method on diff with the 2 heads. And then I call the tail delta on the 2 tails. Okay? In Shapeless, once you've written the types, the implementation is obvious because it's almost the only way you can write things that compiles, given these types. So the hard stuff is to get the types right. Okay, and finally, I define a convenience method, apply, that takes 2 objects of type A, grab their generic representation, and pass this generic representation into a simple delta. Okay? Oh, sorry. Okay. So let's try that. I define 2 classes, address and character. There is an address into the character. And 2 instances of character. And I want to compare those. So if everything works, I can do something like that. And okay, that's quite classical in Shapeless. The type is bigger than the value. That's normal. And so if we look a bit hard, we can see that Homer and Ned have a different name, of course. They have the same age. And they have a different address. Okay, so far so good. Still easy? Yeah? Great. So that's nice, but if we get back, we see that they have very similar addresses because they are neighbors on the same street, but our simple delta just tells us that they have different addresses. We would like to go into the address field and compare the fields of the address, rather than comparing the whole address. So we can do that. So again, we define depfn2, we call it delta. We constrain its output type to be a HList. We define our aux alias, the HNIL case, like before. And now we are telling a little bit, it's a little bit more complicated, but what we are telling here is that given 2 non-empty HLists, if there is a generic representation for the head, and if I am able to compare, to compute a delta for these generic representations, and if I am also able to compute a delta for the tail of the representation, then I am able to compute the delta for the whole list. Okay? And the types are quite obvious. The output type will be the output type of the nested delta followed by the output type of the tail delta. Okay? It just go 1 level deeper. And again, the implementation here is obvious. You don't have a choice. That's the only thing you can write. The problem is there are types that do not have generic representations. String, ints, doubles, Java types. And so they wouldn't be handled by this type class if we don't add some case. But on the other hand, if we reuse the hconst delta from just before, there will be an ambiguity because a type that has a generic representation can also fall into the case where we don't need a generic representation. And so there will be an ambiguity. And as you know, if there is an ambiguity when we are resolving implicits, the compilation phase. Fortunately, there is a trick that we can use. It's here. We can put the list-specific case into a trait and make our object extend this trait. Because it's how the implicit resolution works. When the compiler is searching for an implicit, if it doesn't find it in the current scope, it will then go up the type hierarchy and try a subtrait to find its implicit. So in the case where we have a generic representation for the head, it will call this. But if the head is int or double or string, it wouldn't find it here, and then it will go up into the low priority delta. Okay? And finally, as before, we add our little convenience method so that we can call that from the outside without calling the implicit ourselves. And so now, of course, I have an even bigger type because my delta is more precise. And it says that Homer and Ned have different names, the same age. And if you look there is a nested HList into my HList that tells me that they live in different numbers on the same streets in the same city. Okay? We will not see anything other than that. Okay, so we can relax. Of course, there is much more out of it in Shapeless. There are this coproduct thing that it's the dual of HLists. So along with HLists and coproduct, we can represent any case class or family of case classes. There is a thing called singleton types that enables labeled generic. It's a generic representation where you keep the names of the field. So it can be very useful, for example, if you want to serialize to JSON, like for free. There are extensible records. So you can take two classes, merge them together, and obtain another case class. Polymorphic functions, type class derivations for people who want to not write themselves their type class implementations, and so on and so forth. Okay, so yeah, I have 5 minutes left. So I have time for a little bonus. Imagine now I want to make something real with my delta. For example, I want to take a delta and apply it to another object. So that's of course doable. Like before, I won't get into details, but I define a type class patcher that takes a generic representation of an object and a delta, modifies the generic representation using the delta. It's here. If in the delta I have an identical, I don't do any modification. If I have a difference, I apply the left value, the right value, to modify the representation. And finally, I get back a modified representation that I can convert back to my class. So if that compiles, yeah, I can, for example, transform. Let's compute the delta first. I can transform Homer into Ned. It's simple. I take Homer, and I apply it the delta, and I obtain net funders. I can have Bart. Let's say 10, and he lives in Homer address. And I can move Bart, morph Bart into Ned Flanders, which is evil. But of course, since in the delta we had an identical for the age, so when I apply the delta to Bart, I obtain a younger Ned Flanders. Okay, so that's pretty much it. Do you have any question? We have 3 minutes left. Yes?
Do I have to provide the values if I'm creating a buffer for, I mean, the values that are identical? Can I sample omit them?
You could. So the question here was, are we obliged to provide a value here for identical? Couldn't we just omit it? You could, but you wouldn't be able to write a patcher then, okay? Because you will have a hole. See what I mean? When I do the patcher, I align a representation for Bart and a delta, and if there is a field missing in the delta, the both wouldn't align.
Okay, so the shape would have to be the same, but I could possibly omit values, right?
Yes. In fact, you could do this with label generic, which is the kind of generic that retains the field names, and then you could align using the field names and do some magic, but it wouldn't fit in a slide.
Okay.
Any other question? Yes?
You mentioned label generic. It's, as far as I know, it's just generic with labels, right? And then the types of the fields of the generic, right? If I get it correctly.
Yes.
Is it possible to filter out, for example, the field names with a specific type? If you have, for example, if you have a case class which has some fields which are strings and some are options, and you want just the strings, is it possible to do?
Yes, of course. You have type classes in the end, generic or label generic is most probably a HList, and you have there are type classes in Shapeless to filter out a HList given a type or something. Okay, this is the label generic. In green, it's only the type, so it wouldn't have fit in a slide. But you see, it's there's a little compiler trick that makes the name into a type, the name of the field into a type. But we don't have time to elaborate on that. Just a last thing. This year we are reviving Scala I/O in France, late October. The call for paper will be open by the end of the month, and we'll be happy to see you there. Thank you.